In this nutshell, I introduce microcontroller interrupts. I explain what they are. I describe polling versus interrupts. I show how interrupt routines are called and how interrupt subroutines are called. We show the interrupt vector table and how you enable interrupts with global and local enables and the use of the interrupt library. And remember, if you do find this video useful, please like and subscribe. Microcontrollers will need to respond to events. We have internal events, which are on-chip peripheral devices, or an external event, such as a button press. So there are two methods that we use to detect if an event has occurred. They are polling and interrupts. So we have looked at polling before in our code, and we will continuously check a flag or an input pin and respond when a change is detected. What we're going to look at now, though, are interrupts. So they are triggered by hardware, and they cause the CPU to pause what it's currently doing and to execute a routine called an interrupt service routine. So a simple analogy between polling and interrupts: you're at a movie, a cinema, watching a movie, but you are also waiting for a text message. So using polling, you need to actually sit there and check your phone to see if the message has arrived. So if you have to check it frequently, then the flow of the movie will be affected because you're always looking down at the phone. If you are only checking your phone infrequently, then you may be a while before you actually realize you have a text message. Now, looking at interrupts, we can put the phone on vibrate, and we only check the phone for messages when a vibrate/interrupt occurs. So we don't need to constantly look at the phone, and we can respond immediately when the text message arrives. Reviewing polling, which we have used before, the software periodically checks the system flags or external pin states using an if or while statement. And polling is fine when you don't have much else to do or timing is not critical. Now, if we use a while loop, then all the other tasks are blocked until the event occurs. If we use an if statement, then the event may be missed, or we may have a late response unless we check it frequently. So here's an example of polling here. We check, this is checking to see if the button is pressed. So we're polling pin A bit 0, and then we wait for the transmit buffer to become empty, so we're locked up here waiting for the empty flag. So the advantages of polling: it's easy to implement, and the order in which we check the device is dependent on software. The disadvantages are we have slower response times, and we have software overheads as the CPU is spending time to check if the device needs servicing. So looking now at interrupts, the microcontroller hardware is monitoring the onboard device flags or external pins on the microcontroller, and the hardware itself will call a subroutine when an event occurs. So this subroutine has a special name. It's called an interrupt service routine, ISR. Sometimes people call that an exception handler. So the interrupt is actioned automatically by the hardware, so the software doesn't have to do any polling to see if an event occurs. When the interrupt occurs, the hardware will pause the CPU and get it to call the interrupt service routine, which has a code to handle the event. When the interrupt service routine is finished, the CPU goes back to where it was in the code before the interrupt occurred. So the advantages: we have immediate response to an input-output request, and there are no software overheads that polling would require. Some disadvantages: the priority of the interrupts is fixed. Plus, the interrupt will temporarily halt the main program, which might disrupt the task you were executing. It does take time to store and retrieve the program counter and registers onto and off the stack. If you are using multiple interrupts, you need to be careful how they are managed. And if they are heavily used, such as a timer, they can consume CPU time. Plus, we can have combined interrupt and polling. This is often found using external interrupts, where we have two or more devices connected to a single interrupt line. This is called wire-ORed, or if we are using the pin change interrupts. If we're doing this, then after the program is interrupted, you must poll the I/O devices to see which device caused the interrupt. Now, to understand subroutines. Subroutines are sections of code that are grouped into a packet called a subroutine. And this is called from the main program. So when compiled, the subroutine code is given a memory location, and the subroutine starting memory location is placed into the machine code call instruction. So when the subroutine is called by the CPU, it knows the starting address of the subroutine. But we must remember where the call came from so that we can return to that point at the end of the subroutine. So it does this by using a program counter. So looking at the program counter, the CPU follows a fetch, decode, execute cycle, where we load and run the instructions stored in program memory. The memory location of the next instruction to be executed is stored in the program counter, and after the instruction has been executed, the program counter is incremented by 1 to point to the next instruction in memory. That's because the instructions are placed sequentially in memory. Now, if the instructions are non-sequential, i.e. we had an if, a while statement, subroutine command, etc., then the PC is loaded with the new instruction memory address, and that will cause the CPU to go to a different part of the program. So the operation of the subroutine: when the subroutine is called, the CPU saves the program counter and general purpose registers onto the stack. This is just temporary memory. The program counter is then updated with the subroutine's address. That's part of the call instruction. The subroutine is run, and then when the subroutine is finished, the saved program counter and registers are restored from the stack. So the code execution resumes from the instruction following the subroutine call. And note, you can pass parameters to and from the subroutine using the stack. So now looking at interrupt service routines, ISRs, and how they work. So unlike the subroutine, which is called by software within the code, the ISR is called by the microcontroller's hardware when the interrupt condition is met. So because the interrupts are called by hardware, the address of the ISR cannot be put into the machine code as it is in a subroutine call. Instead, the service routine starting memory location is stored in a table called the interrupt vector table. So when an interrupt occurs, remember, it's called by hardware, the microcontroller uses the vector table to find the address of the corresponding ISR routine. So when the compiler compiles the code and downloads it into program memory, it also knows the address of the ISR and puts that into the appropriate position in the vector table. So if we look at how the operation occurs, the program's going along normally, a hardware event occurs. That could be an external pin change or an internal flag is set. The global interrupts are disabled. This stops other interrupts from occurring. The current CPU instruction is finished. The CPU program counter and general purpose registers are stored into temporary memory called the stack. Then the address of the ISR is fetched from the interrupt vector table and put into the program counter. The ISR is run until completed. Then when it's finished, the previous program counter and general purpose registers are restored from the stack. Global interrupts are re-enabled and the program runs from where it was interrupted. Now, looking at the interrupt vector table, the ATmega 2560 has 57 separate interrupt sources. They include on-chip peripherals such as USARTs, ADCs, etc., and external interrupt pins, which are the external interrupts and pin change interrupts. So each source has a vector in the interrupt vector table, and that holds the 16-bit memory address of the start of the ISR. During compilation, the compiler stores each ISR in program memory and records the start address in the appropriate vector in the table. So when the code is downloaded, both the program code and vector table are updated. And we can see the vector tables here. We have a reset vector. We have 8 external interrupt pins. We have 3 pin change pins. And as we go down, we can see a watchdog timer, timer 2, timer 1, timer 0, SPIs, USARTs, analog comparators, ADCs, EEPROM, timers, USARTs, TWI, etc. So all of these on-chip peripherals that have interrupts have an interrupt vector in the interrupt vector table. So when using interrupts, they need to be enabled, and that is performed at 2 levels: a local interrupt that's specific to the source, and a global interrupt that's for the whole processor. So each hardware interrupt source has its own interrupt enable bit in a control register. When we set this bit, we turn on the local interrupts. Now by default they are disabled on power on or reset. Note, even though we enable local interrupts, no interrupt will trigger unless the global interrupt is also enabled. So think of the global interrupt as a master switch. It's in the AVR status register. If it's disabled, no interrupts will be serviced, no matter the local enable settings. And we can enable global interrupts in 2 methods. We can use C functions, SEI to enable interrupts and CLI to disable interrupts. If we are using these, we must include the AVR interrupt.h library, or we can use inline assembly, ASM, SEI, ASM, CLI. So if we see the local and global, we can see that the global here, imagine there's these lights on, we can turn local interrupts on, but the light won't come on until the global interrupt is enabled. So when you are using interrupts, you should first enable the local interrupts, get them all set up, and then enable the global interrupts. Now, if global interrupts are disabled, that will occur during an interrupt service routine. The new interrupts that will occur whilst disabled will remain pending, and then when the global interrupts are re-enabled, these interrupts will occur. When using interrupts in your code, you need to include the AVR interrupt library. This library has certain functions such as enable global interrupts or disable global interrupts and other features as well. It also allows you to specify the interrupt vector for your interrupt service routine. It does this by this command, ISR interrupt name vector, and we can get the name of the interrupt from the vector table. So there's some examples shown here. We had the ATC interrupt vector, timer 3 compare A interrupt vector, external interrupt vector 4. Now note also, then you can't pass variables to and from the ISR, so they must be declared globally, but also you must declare these variables volatile, and that prevents the compiler from optimizing these variables that can cause errors. When you're writing an interrupt service routine, you want to make the code short and fast. So to do that, minimize the code in the interrupt service routine, avoid loops, delays, whiles, or heavy computations. Don't ever call a subroutine within the ISR. If the ISR code is long, then rather than putting the code into the interrupt service routine, set a flag inside it, and the flag can be actioned in the main program. Avoid functions that take a lot of time, such as printf, and because you can't pass variables to or from the interrupt service routine, they must be global and they must be declared volatile. So note, when an interrupt occurs, the microcontroller will automatically disable the global interrupts, and they will be re-enabled after the interrupt is finished. So this is used to prevent nested interrupts. So if an interrupt occurs while the global interrupts are disabled, they're not lost. They will just wait pending, and when you re-enable the global interrupts, they will be actioned. If interrupts occur simultaneously, the interrupt with the highest priority will be run first, and you can look at the priority by the order of the interrupts in the vector table. And remember, because you can't pass parameters to or from the ISR, the variables must be declared globally, and they should be declared volatile to prevent compiler optimization producing errors.